So maybe you all can enjoy a bit at the year end. And your exams is in February, right?
Yes, sir. February
Right.
15
Eh,
or 16. What is the
Okay.
date, Surinder?
So anyway, let's see. I mean, it's February, so you have like
Sir,
at least
16 or
yeah.
17.
Okay, so you have at least 1 month of practicing, because I may have like 3 or 4 lectures left out, nuclear reactions mainly, and all these problem sets that I am giving. So you try to do it very well, and the solution sets that I'm sending, you try to compare what you have done with the solution sets that I am giving, because it is, I mean, the goal is not only to do the solutions, but the goal is to do the solutions in the most logical and the lucid and in the most compact form, so that you have ample
Sir,
time
there
to
is a
finish off
problem.
your question papers. Yeah.
Sir, I have a question. See, there was a question that in a deuterium problem, if there is that much of the depth, what will be the energy? So we will use that cot hyperbolic formula, sorry, cot formula
Yeah.
of
Yeah.
something equal to root over of E by V naught minus E. That was the question. So
Mm-hmm.
it was some V naught, and it was asked to find out the E. So the
Mm.
only way we can use find out that by computing. I mean, for computational method like Python or C++ anyway. But in your solution, it was nothing mentioned about it. It was something like that. There was some points of V naught and there were some points of E naught. For that value of V naught, what will be the value of E naught? And you said that by comparing this is the closest value of V naught, so this will be the closest value of E.
Yeah, I do not fully remember the question, but it may be that we have taken like sets of values, so that if the value is this, and then the value would be that. So I think there was some series of values from there. I think there was some approximately you can conclude about that. So obviously nobody is going to ask you to write a program to do the solutions, but in some of the questions it may so happen that you have to take into some approximate values to arrive at an approximate result. So I will look into it in further details, but I don't think that you have to write a program for that, because if you just I mean, if you assume some value, that will give you some results. So if you now, it's like a kind of a drawing a graph. So if it's like the 3 or 4 values for x you are taking, what will be the value of the function? It may be something like that, but obviously nobody is going to write a program for that. So I will have a look at it, and I'm writing it down, this deuteron problem. So where it was in some problem set, is it in some
In,
problem set?
in
Yes, sir.
problem set, there was two question.
Okay,
Problem
so what I suggest is that you send me an email, just one of you, just send me an email mentioning the problem set and the problems that you faced actually doing that, just in a compact 1 or 2 lines, just so that I remember that. So I'll try to attend to that. If I have the email, I will remember it. Otherwise, I may forget. So just send me an email with the problem that you faced. You may even scan some things to make me understand that this is what we faced. So you can just scan an image and just send it as an attachment to the email. So no problem at all. So try to do that. But obviously, as far as I remember, there was some kind of question is like if you put in some values, you can arrive at the value of the function. So just let me know by an email. So and the solutions, I think, how many solutions did I send to you?
up to three, up to three.
Up to
Because
three.
yeah, so sir, please wait till 1 or 2 days. We will try to do the problem set 4. Then you please send the.
Yeah, that's it. And I, as I said repeatedly, that even if you are late, try to do the problem sets on your own first, and then only see the solutions. Otherwise, if you once see the solution, you will never learn. So you try all means to do the solution yourself, and then only you see the solution. And this whole month of January, I will ask you to practice it again and again and again without seeing the solutions. If only if you face problem, then only you'd see the solution sets. Because I mean, uh, sometimes questions come which is like you are using the basic concepts that you used in doing the problem sets in the problem sets, but the questions might ask you something which you may require the practice that you have done with your problem sets, but you it might require to do you uh, conceptually on something. So that the main theme is that you have to have your concept absolutely clear. Otherwise you may face problem, you will have difficulty doing the problem. So practice it again and again and again and again and again, so that what happens, if you practice it once, you may be clear at some point. But if you practice it 10 times, your clarity will be much more. And then it will be very, very easy for you to do the problems in the examination or even in some competitive exams. So try to grow your concepts absolutely well, absolutely clear. And as I said, that these lecture notes, always my students have told these lecture notes are very, very useful. Because if you just pick up a nuclear physics book, there is so much of information. Particularly before an exam, it is very difficult to go through a book of maybe 1,000 pages. It is absolutely not possible. So you need a summary where all the mathematical expressions are there and all the concepts are there in a very precise and concise manner. So this lecture notes is aimed to address that. You have all the concepts in a very compact, maybe 100 slides. That's the whole of your nuclear physics course. So if you go through the slides, your concepts are absolutely clear, because you have to go through the slides again and again, so that there is absolutely, your concepts are very, very clear. Then only you will be able to do the problems. So both the lecture notes and the problem sets, you practice again and again. That will be very helpful for you to do good in your exams. And most of the time I have found in nuclear physics particularly, all of my students have always done well, because they have always come to me and said that, sir, your lecture notes are very useful, and we have practiced the problems and solutions very, very my time and again. So that actually helped during the exams very well. And not only, because my goal is not to prepare you for the exams only, because you have to be prepared for your competitive exams as well. So your primary goal should be to grow your concepts very well and practice the problems as many times as you can. And then after, over and above that, if you have time, you can obviously do the problem sets from, as I said, from Cohen you have very good problems, and from Crane you have very good problems. Even you can practice the problems that are worked out in Crane also. So that will help you a lot. But before the exams, it is always good to to go through the lecture notes and the problem sets time and again. So is it clear? Everybody got the point? What I mean to say?
Yes, sir.
Yeah. Okay. Okay. So what I will do is that I will go through parity once again today, because it is an important concept. So our since next Wednesday I'm not going to take classes, the December of 30th. So what I will do is that I'll do the parity, these concepts, and the parity violation, and then I will go through 2 slides of nuclear electromagnetic transitions, and then I will do a little bit of the liquid drop model. And then when we come back next year, I will revise the liquid drop model and start the lectures and finish with the nuclear reaction. So maybe another 3 or at most 4 lectures, I will finish the course. The rest of the lectures you will be there to practicing the stuff. So in between, so in the month of January, you totally keep the month of January for practicing the stuffs. And when you're in your holidays, if you have time, this next week, just go through the problem set and the lecture notes at least once. So that will help you a lot. Okay. So let's start with parity again. So as I said in the last lecture, so you can see, all of you can see the slides.
Yes, sir.
Yeah. So as I said in the previous lecture, so what is, if you've been asked about the concept of parity, many students don't have the concept of parity. They just do it mathematically, just like a robot, they just do it. but it should not be like that. So you have to have an absolutely clear concept of parity. So as I said, in the macroscopic world, we parity is violated. So as I said that our most of our hearts are in the left hand side. So but there are some people in the world, maybe one in million, whose heart is on the right side. So nature has actually made a distinction. So it's not valid in the macroscopic world. So basically parity is, what I said is that mirror reflection followed by a 180-degree rotation, so that you have x, y, z as the coordinates of anything, and to do a parity transformation it just comes out to be minus x minus y minus z, because this is what is useful to deal mathematically, because mirror reflection, only mirror reflection is difficult to handle mathematically. But mathematically, if I do a space inversion, that is minus x minus y minus z, that is easier to handle, and so that is actually a parity transformation. So in atomic and nuclear physics particularly, the laws that we see in macroscopic world, the law of conservation of energy, linear momentum, angular momentum, those all things are valid in the microscopic world also. But in addition, in the microscopic world, we have conservation of parity. That is, a system is equal to its own mirror image. Okay. Now, uh, here, while developing the concept of parity, the concept of helicity comes up. Like a human being or a helix is not equal to its own mirror image. As I said about the heart, say it's in the left side. So it's thus systems that are not mirror symmetric, so in the mirror it's not symmetric, are said to possess helicity. So we have helicity, like if I am a right-handed person, I'll say it as right-handedness, or if I am a left-handed person, it is left-handedness. So they, in the macroscopic world, they do not have a definite parity. Okay, now just a moment. Okay. Okay. So parity conservation, as I said, in quantum mechanics means that two physical systems, one of which is a mirror image of the other, must behave in identical fashion. So in the microscopic world, we expect that this is bound to happen, because nature simply cannot distinguish between the left side of an electron and the right side of an electron, or a left side of a proton and the right side of a proton. It should not be like that. So parity should be conserved. So in other words, parity conservation implies that nature is symmetrical and makes no distinction between right and left-handed rotations or between opposite sides of a subatomic particle. So as I already said, that parity transformation is basically a space inversion, that is a mirror reflection followed by a 180-degree rotation parallel to the mirror. And I say that mirror invariance actually implies invariance also under a parity transformation, because you are just rotating, there is only a 180-degree rotation parallel to the mirror. So basic ingredient in the parity transformation is the mirror reflection. That is the main ingredient into it, and that 180-degree rotation, it does not does not disturb very much. So it is, you can just add it. So basically, main thing that you have to understand is the mirror reflection. So if it's mirror symmetric, it should be also symmetric under parity. The parity should be conserved if it's mirror symmetric. Okay, now I already talked about this experiment. So have you all seen this? When I send the lecture notes, have you again thought about this experiment in the mirror? Have you thought about this?
Yes.
Yeah. So again, I'm saying that in the macroscopic, macroscopically, if we see it, so we are seeing that the direction of the current is towards the mirror, and the magnetic needle is rotating in a particular direction, Maxwell's corkscrew rule. But in the mirror, I am seeing the rotation of the needle is in the same direction, but the direction of the current is now reversed, because it is coming out of the mirror on the other direction. Both the real current and the mirror reflected current are in opposite directions. So actually here, macroscopically, the experiment that we are seeing it in the mirror should not actually happen, right? It cannot happen actually, because then Maxwell's corkscrew rule will not hold. But if we look at it much more carefully, we look at it the microscopic way, if you see the microscopic picture, the this I mean um, in the atomic scale, what we are seeing, the spinning electrons, if we see it in a particular direction in the actual world, in the mirror reflected world, the spins are just reversed. So that results in the inversion of the pole of the magnetic needle. So in the actual world, we are seeing there is top is south, bottom is north, but in the actual mirror reflected world, we see that the top is north and the bottom is south. So then actually in this way, the directions of the current will be in reverse, and when this current I is away from the mirror, but since the rotation of the electrons is in the other way, so that results in the magnetic poles got inverse. So that is valid according to Maxwell's corkscrew rule. So here we find the mirror image of the experiment can actually be performed, so that all the physical laws holds for the mirror image of the experiment. So here we see parity is not violated. So we can see that the law of conservation of parity is not violated on the atomic scale. If we consider it macroscopically, then this is not valid. But if we consider it microscopically, then this is valid. So parity is not violated. Is this clear to everybody? I would say absolute crystal clear. Is it clear to everybody?
Yes,
Hello? It's clear? Everybody? All
yes,
of
sir.
you just say yes or no.
Yes, sir.
Yes, sir.
Yeah. So you understood it absolutely clearly, right? So this is very, very important. So now you think it over, how parity comes up in our life. Okay. So now this famous experiment that led to Nobel Prize is this. I mean, before going to the experiment, I just explain a little bit about this parity violation in weak interactions. Okay. Now you have a picture in the left hand side. So here you see an ellipsoid which represents a large number of cobalt nuclei. So you have an assembly of cobalt nuclei, all with their spins in a particular direction. So when I mean all of their spins in a particular direction, you have a spin alignment of most of the nuclei in a particular direction, but you may have a small number of nuclei whose spins are in the opposite direction. Aligning means, it does not mean you have 1,000 nuclei in an ensemble. Aligning means does not mean that you align all of them, that is all the 1,000 nuclei in a particular direction. Aligning means you have aligned them, most of the nuclei in a particular direction, but obviously there may be few of them whose alignment is in the opposite direction. So here you can see that most of the, I mean, the spins are such that that most of the beta rays are emitted downwards, but some of the beta rays are emitted upward as well. But that means it is aligned in such a way that most of their spins are in a particular direction, the red arrow you are seeing. So their spins are in a particular direction that leads to emission of beta particles, mostly in the downward direction. Now on the right hand side, you see the process in the mirror. Now what happens? The direction of the spin is now reversed in the mirror image, while the direction in which most of the beta rays are emitted remains unchanged. Okay, so you have most of the beta rays in the mirror image also in the downwards, but the spin has got reversed. Okay, so you can distinguish this because it is the spin has changed and the direction of spin has changed, but still it is downwards. So you can distinguish the real world with the mirror world. Okay, so the mirror world becomes the inverted or parity transferred world by turning the mirror image upside down. Now if you just change the I mean, if you give a 180-degree rotation, now what happens? The spin of the nuclei will become the same. Now in the mirror image you are seeing the a particular direction of the spin, the red line arrow. But if you just rotate the mirror by 180-degree, that spin will become the same as the original world. because it reverses. But then what happens? Another thing will happen. Now the most of the beta particles will be emitted upward in the mirror image. Is it clear to everybody?
Yes, sir.
Can you repeat the
Yeah.
last line, sir? Can you
Yeah,
repeat
so
the?
you are seeing the real world. It is difficult to make you understand just by voice. You have to use a little bit of your imagination, because in the physical class I would have drawn a lot of pictures, and then with hand waving, I mean with my movement of my hands, I would have made it a little bit clearer, but we have to get accustomed to it. Now you concentrate on the direction of the red arrow in the real world, that is which is written here as this world. So in the real world you are seeing the direction of the red arrow in a particular direction, but in the mirror image you see it's just opposite. The direction has just reversed. Is it clear?
Yes, sir.
Yes, it is clear.
Now, yeah, now if you give the mirror a 180-degree rotation, what will happen when you give the mirror a 180-degree rotation? So what will happen is that the direction of the mirror image, you have the mirror image. Now the mirror image, you give a 180-degree rotation to the mirror image. If you give a 180-degree rotation to the mirror image, the direction of the spin, that is a red arrow, will be reversed in the mirror image, and it will be become identical to the direction of the real world. Is it clear?
But sir, where will be the observer and what will be the axis of rotation?
observer Observer is just the same. Now you consider the mirror image as some kind of portrait. You consider the mirror image as some kind of portrait which is fixed. Okay, now when I see this, you just fix it. Okay, it's you just
Sir,
draw the mirror image. You just draw the mirror image on a page. Okay, now that drawing you give a 180-degree rotation. If you give the drawing a 180-degree rotation, what will happen? Now most of the beta particles will be upwards, and the spin will change and become identical with the real world, because the direction of the red arrow will again be changed if you give a 180-degree rotation. Is it clear?
yes, sir. I think the rotation will be the axis which is passes through the small side, so that it will be reversed. Yes, now I got it.
Because it is the rotation axis is the same as parallel to the mirror. Okay, and the real world, that is fixed. The real world, this world which is written this world, it is fixed, and you are seeing the mirror image in the mirror. Now once you see the mirror image, you just fix it. That means in other way, you just take a picture of the mirror image. Once you take a picture of the mirror image, you just paste the picture on the mirror itself, so that it is the mirror image. Now you give a 180-degree rotation to that mirror image. If you give a 180-degree rotation to the mirror image, most of the beta particles which is in the mirror image, now it is downwards, it will go upwards, right? It will go upwards, like you are seeing one, two, three, four, five green balls you are seeing downwards. It will go upwards if you give
Got it.
180-degree rotation,
Yes,
right? But
yes,
also another thing will get changed. That red arrow, the direction of that red arrow will get changed. It will be just opposite, because if you are giving a 180-degree rotation, this goes up, these seven balls goes up and two balls come down, and the red arrow, the direction of the red arrow just becomes opposite. Opposite in the sense, now it becomes identical to the direction of the this world. Is it clear?
yes,
Just draw
sir.
it and
Yes,
just
sir.
draw it and invert the page. Draw it and invert the page. Clear?
Yes, sir.
Now what happens in the parity
Now it
transform
is
world?
clear,
What
sir.
Yeah. So now what happens in the parity transform world, because you have given 180-degree rotation, so what you are seeing in the mirror is a parity transformed world. Now in the parity transform world, what happens? The real world and the parity transformed world, the spins are same direction spin. But in the parity transform world, the seven green balls are in the upward direction, while in the real world, the seven balls are in the downward direction. Downward direction. So in this case, you are saying that parity is not conserved. Is it clear?
Yes, sir.
Okay, so if you read it out, the mirror world becomes the inverted or parity transformed world by turning the mirror image upside down. The spins of the cobalt nuclei are thus returned to their original direction, but most beta rays are now emitted upward, contrary to experimental fact. So the parity transformed world is not identical with the real world, and parity is not conserved. So this is the basis for the experiment that Li and Yang has performed, which has led to one Nobel Prize. Okay, so parity, what we find is that parity is not conserved in weak interaction. That is this beta decay, it is a weak interaction, and there we are seeing that parity is not conserved. So what they did in the experiment is in the next slide. So what actually they did, that the experiment concerning this Li and Yang in 1956, they did this experiment, this parity violation in beta decay, which led to Nobel Prize. So the experiment that they did is they're concerning the angular distribution of beta particles emitted from aligned cobalt 60 nuclei was carried out. So they actually measured the these beta rays as well as gamma rays in the equatorial detector, in the equatorial counters. There is a detectors placed in the equatorial plane as well as in the polar plane, and they have detected both the beta and the gamma rays. So what happened when they heated up the when they first aligned the nuclei in a particular direction, that is their spins are in a particular direction, as I showed in the last slide. So their spins are aligned in a particular direction, so most of the beta rays would be emitted in a particular direction, and now they started heating up the nuclei. Now once you heat up the nuclei, what happened, their spin alignment will be disturbed, and so they will become sort of non-aligned nuclei. So in both directions there will be same number of beta particles emitted. So that's what they actually found in this curve. Can you see this curve now? This
Yes.
1122
Yes.
Yes, sir.
results of parity experiment. So you can see, you see in the x-axis it is time. So gamma anisotropy, it's one thing, and in the beta anisotropy you are seeing that there is this anisotropy in the 0 to 6 minutes. You are saying there is anisotropy in the equatorial counter relative to the polar counter. While when we started heating up, after 6 minutes to 8 minutes, you are seeing that both these lines merge in a single line. So with a value 1. With a value 1 means there is no anisotropy between gamma equatorial plane detector and polar plane detector. So once you heat up the nuclei, their spin alignment is destroyed, and they started emitting beta particles same in the both the upward and downward directions. But when they were aligned, there is this huge anisotropy. So we are seeing that parity is violated. So the number of beta rays emitted in the upward direction is not the same in the downward direction. So they found is that the polar gamma counter rate lower than the equatorial counter for both field directions as expected, but the beta counter indicated that more electrons were emitted in the direction anti-parallel to the angular momentum vector than parallel to it. This is proof of parity violation in the beta process. Now the main issue is how come there is parity violation in the weak interactions? Why actually there is parity violation? Now if you remember that in beta rays emission, so there were the emission of the neutrino or anti-neutrino, because initially people did not know about these neutrinos, and people thought there is emission of two particles, the neutron and the beta particle, or the proton or the beta particle. So there is this emission of the third particle was not known. So Niels Bohr went to the point of even saying that conservation of energy is not valid in this case. He went to this extent, because people could not even thought that there is emission of such a particle which is neutral as well as almost zero mass. And Pauli actually postulated the theory of these neutrinos twice, actually 1930 and 1932, I think, or 33. So he postulated twice that these are neutrinos, which are small neutrons having very small mass and neutral in character. So this neutrino or anti-neutrino is actually the culprit for this parity violation. So what happened is that the results of the experiment involving helicity in weak interactions, helicity because parity is not is violated, point to the neutrino or antineutrino as a culprit of parity violation. Now the antineutrino involved in beta minus decay is presumed to have its angular momentum vector aligned with its momentum vector. So it moves as a right-handed screw. So as you do use your screwdriver, you use the right-handed screw. So the neutrino, the antineutrino actually moves like a right-handed screw, while the neutrino moves as a left-handed screw. Now to make this alignment, there is this parity violation. For it to happen, most of these beta particles are emitted in a particular direction because you have to conserve momentum. So if the neutrino behaves like that, that it has to move in a particular direction, then to conserve momentum, the beta particle has to be emitted in a particular direction. And that actually led to parity violation. Do you understand this? I'm taking just 1 minute off because I have an urgent call to handle. Just think about this thing. I will get back to you. Just 1 minute. Okay, can you hear me? Okay. Hello.
Yes, sir,
Yes,
we
sir.
can see you.
Yeah. Okay. So did you get my point? So since the neutrino or the antineutrino has to move as a right-handed or left-handed corkscrew, so actually it will move in a particular direction so that its angular momentum and momentum is in the same direction or in opposite direction. Now, if this neutrino is defined by this, then actually to conserve momentum, the beta particle has to be emitted in a particular direction. That is the beta minus in a particular direction and the beta plus in another direction. So that leads to the beta particles emitted just as I showed in previous figure. Say in the upward, it's emitted more in the upwards and less in the downwards. Though this is the reason this neutrino or antineutrino is actually the culprit of this parity violation. Now, did anybody has any question about on this parity violation?
No, sir.
It's clear. It's clear because we are in one slide. We are actually discussing one Nobel Prize, so it's hugely important, and it appears that it's very easy, but you can understand that years of work has gone into this to understand this concept. Okay, so it is really very interesting. Even actually at that time, it's in 1956, so you can understand the concepts of nuclear physics are being grown during that time. So people did not know about all these things, and people initially thought there are two particles emitted, and then suddenly this concept of neutrino came up, and then after this neutrino concept came up, then there is this parity violation that this neutrino is such a strange thing that its angular momentum and momentum has to be aligned. Either it is parallel or anti-parallel, so it has to be aligned. So that is another very strange property of the neutrino. So and that leads to this emission of the beta particles in a particular direction, and that leads to parity violation. Okay, clear? So let's move on. Okay, so parity violation done. Now we will discuss. I mean, it's very short. I will just discuss in two slides. Nuclear electromagnetic interactions. So it is. There's, as I said, this nucleus is a very interesting thing because it is compact in size. Its size is very attractive. Femtometer, 1 Fermi, 2 Fermi, like that. And also, this is the only place where you see all the four forces working. So you have strong force, you have electromagnetic force, you have the weak force, and you have gravitational force. Now gravity, we have not dealt, I mean, we have not discussed anything about gravity, but that is very obvious. If you have one proton, one neutron, they will be attracted by gravitational force as per Newton's laws of gravitation. Now we have discussed the strong force quite a bit about how it interacts in case of deuteron, and we will later on see how it, in case of neutron-proton scattering or proton-proton scattering, how it works. We have studied the weak interaction through beta decay, but we have not studied yet the electromagnetic interaction, how it happens inside the nucleus, and how it interacts with the nucleons. So that's what we are going to study now. So we would study the emission and absorption of electromagnetic radiation by nuclei. So its nuclei do not only interact with strong force, they also interact with the electromagnetic force as well, because they have charges. Okay, and the neutron is neutral, but you have non-trivial charge distribution inside a neutron, so it has a magnetic moment. We have seen that neutron has a magnetic moment, so it will definitely interact electromagnetically as well. Okay, so in atomic system, we deal with radiation usually in the visible or UV region, and lambda is 100 or even 1000 times larger than the size of the atom. Thus, it is generally possible to restrict considerations to electric dipole radiation. This is interesting because you have studied the atomic case and you have studied the electromagnetism mostly in case of atoms. So, and you have dealt with only visible or UV regions. And it's about angstrom. So that is about 1000 times larger or 10,000 times larger than the size of an and lambda is 100 or even 100,000 times larger than the size of an atom. So you have like sodium lines, so 5000 angstrom, it is like that. But that is generally possible to restrict considerations to electric dipole radiation. But in case of nuclear radiation, since the wavelength has to be shorter, we have to deal with emission of gamma rays. The energies are above MeV, while in atomic case you have EV or KeV, like that. But in case of nuclei, we have to deal with million electron volts, and the wavelengths are much shorter than in the atomic case. However, if we compare them with nuclear dimensions, they are again at least an order of magnitude larger. They are still larger. Even so, it turns out in the field of nuclear physics that only in special cases is the electric dipole approximation sufficient to account for the situation, and in general it is necessary to consider higher multipoles. So you have to consider higher multipoles in case of nuclear physics, while you have mostly dealt with dipoles in case of atomic physics. Now in the case of electromagnetic radiation, we have to deal with oscillating rather than static fields because it's electromagnetism, I mean electromagnetic theory, and we have oscillating fields, right? It's not static electricity. And an expansion can be made both for the electric and the magnetic fields present. So you have studied multipole expansion, and you have to apply some selection rules associated with the emission or absorption of radiation by the various electric and magnetic multipoles. So in this electromagnetic wave, the oscillate, which is obviously an oscillating electric and magnetic field, the electric multipole moments are represented by EL, that is E1, E2, like that, and the magnetic multipole transitions ML. So the most general charge distribution that we'll have is the multipole expansion, and the oscillations of a charge distribution leads to oscillations of each term in the expansion, and the resulting radiation may be thought of as being due to the various terms. So obviously when a charge oscillates, you have these field electric field lines coming out from the charges, either positive, that is the lines are out of the charge, and negative, the lines are going into the charge. So when this charge plus or minus starts to oscillate, the threads, the field lines, you can consider them as threads. So those threads also start uh, oscillating. So that leads to some kind of electromagnetic wave that actually propagates. So since you have done these multiple expansions in your electromagnetism classes, so here you can just simply writing the final terms that the rate of emission of photons can be denoted by this lambda EL. So this is a photon of EL radiation must carry off angular momentum L and parity minus 1 to the L. So this is the expression, and the multiple moments are, you have the Q1 is equal to ZE Z bar, this what is called this dipole vector, and this Q2 the quadruple moment term, and several multiple moments. You have already studied these multiple moments in previous classes. So gamma radiation is emitted when a nucleon jumps from one orbit to another. It is just like an atomic case. But I have actually told you that in case of nucleus, it is difficult to visualize the orbits because it is so compact in size, and how can the nucleons remain in orbits without colliding with each other? Then actually Pauli's exclusion principle helped us, because not all the orbits as classically we expected are valid. So you have only selected orbits. That actually reduces the number of collisions very much. So you have the concept of orbits inside the nucleus. So when a nucleon jumps from one orbit to another, there is emission of radiation. Okay, and so you can represent these as some kind of multiple moments, and you have this electric rate of emission of photons for electric multiple lambda EL, as well as you have lambda ML. But you see that for this EL radiation, the parity is minus 1 to the L, but in case of magnetic case, you have minus 1 to the L plus 1 or L minus 1, whatever be the case. So, and AL is closely related to the amplitude of the magnetic multiple moment oscillations causing the radiation. So it is just like that. Okay. And you have some selection rules as well. So this is important. So changes in nuclear spin, because if one nucleon jumps from one orbit to another, so it will have a change in angular momentum. Okay. So delta I, that the change in nuclear spin, is equal to 0 or plus minus 1. And then parity changes for electric dipole transition. For delta I is equal to 0 plus minus 1 plus minus 2, there is no change in parity, then it's electric quadruple transition. So the change in nuclear spin can take these values. For magnetic transitions, the selection rules are same, but parity rule is opposite. So if you just write it as E1, E2, E3 and M1, M2, N3, you have for EL, II minus IF, initial state and final state difference in spin, is equal to L, and parity is given as delta pi equals minus 1 to the L. But for magnetic case, you have minus 1 to the L minus 1. So you have just a difference between the electric case and the magnetic case. Now, physically, you see why electric dipole transitions do not play such a crucial role in nuclear physics as they do in atomic physics. This is very important. You can be asked anywhere in interview why the electric dipole transition do not play such a crucial role in nuclear physics. Because in atomic physics is so much important, like the antenna and all these cases where electric dipole transition is very important. Because very frequently low line nuclear states all have the same parity. So the transitions between these states cannot be E1, because you have seen the selection rules just above. Since parity selection rule would not be satisfied. So also spins of nuclear states frequently differ quite considerably. So again, low multiple transitions are not relevant. That's why electric dipole transition is not very much important in case of nuclear physics, while electric quadruple transition is much more important. And another thing is important, roughly successive multiple transitions, electric or magnetic, are at least an order of magnitude less probable than the preceding one. So the octupole will be one order of magnitude less probable than the quadruple one. Also, the magnetic transition is in general at least an order of magnitude less probable. That means E2 and E3 and M2, these are of the same order. Right? Magnetic transitions are one order of magnitude lower probability than the electric transitions of the same order. And in any multiple expansion, the next term is one order of magnitude less than the previous term. It's clear?
Yes,
Is
sir.
it clear? Yeah. So this is just, you have to just remember. Some short questions might come out of it, and these selection rules are also important. I mean, this parity in case of electric transition is -1 to the L, while in magnetic case is -1 to the L minus 1. So you see the difference, and why the electric dipole transition is not so important in nuclear case as compared to in atomic case. So this is it for nuclear electromagnetic transitions. Uh, Now, this is nothing, you can just go through it. Now, I will just discuss briefly about this drop model a little bit. Obviously, in the next class, and that is in next year, I will discuss a little bit, I mean, I will revise this a little bit for this drop model and then move on to nuclear reactions. Now, you have always heard that nucleus is considered as a liquid drop. Okay, we have studied many different models, the nuclear shell model, a single particle model, and then nuclear collective model, where the nucleus works like a collective set of nuclei. And here we have this drop model, it acts like a liquid drop. Now you have the stable nuclei that can be transformed by bombarding them with proton, neutron, deuteron. You just hit them with proton, neutron, deuteron. The neutrons been particularly effective because they don't have Coulomb repulsion, so they can penetrate much more. Okay. Now, because if you are bombarded with alpha particles or neutrons, the neutrons can make you more damage, because alpha particles might get stopped even in this one small sheet of paper. Okay, these are, I mean, they lose energy. But these neutrons are highly penetrating. They can penetrate through your tissues and can, I mean, give you a lot of damage. Like, if I remember that when we used to do experiments in TIFR, what happened is that when we stopped the beam, after that we waited for 15 to 20 minutes before opening the beam hole. Can you tell me why? We did not immediately, after stopping the beam, we did not go immediately inside the cave where all these nuclear physics setups are there. But we waited for 15 to 20 minutes. Yeah. What? Yeah. What did you say?
Radiation.
What kind of radiation? Radiation is always there, but what kind of radiation? We actually waited 15 to 20 minutes. So my the answer is actually there in that time limit, this 15 to 20 minutes. What happened is that when we bombarded these beams on the target, and if we have to change some setups, we had to go inside the cave, okay, where the beam used to come. So we stopped the beam and then we went inside. But we waited 15 to 20 minutes before going inside. So what happens when we are tuning the beam, say lithium-7 beam, we are tuning and we are hitting on a target. So when we are tuning, this lithium-7 beam can hit all these metals, right? The beam pipe, stainless steel and all these metals, it's hitting. So when this beam hits, these high energy beams hits these metals, they give out a lot of neutrons. Now these neutrons are highly penetrating. So if we are there during that time, these neutrons will bombard our bodies and will damage our tissues. Okay. I personally was there in the US. Once this experiment was going on, we had to do some setups, but we actually could not stop the beam because that will lead a lot of problems. So I was actually there inside so I actually took radiation for some time, like 5 to 10 minutes. And with me, my boss and some other people also took radiation. So we actually thought that maybe after 10 years we would develop cancer. So I am still under threat that I might get cancer after some time. Maybe after 5 or 6 years I might get cancer. So I actually was irradiated during 2003. And now after that, at least 20 years has passed. I don't know. It may so happen because my colleague Swapanda, who retired, he actually took radiation also because accidentally somebody switched on the beam and they took radiation for like 3 to 4 minutes. They actually ran away, but before that the beam was there. So this actually happened. But nowadays these kind of things do not happen because in those days, and we used to work in university labs in the United States, And in the United States, in the universities, you learn a lot of things because you have to do everything on your own. Because I remember at 2 o'clock at night, I am running the accelerator all by myself. But here in TIFR, they don't even allow you to touch the accelerator. There are trained operators who run them. And there are health physics people. If there is radiation and all this stuff, they will shut down the accelerator. And nowadays, if you work in CERN or in Ganil in Europe, there is no way you can get irradiated because your TLD batch is like online TLD batch, and your access card is like online access card. So even if you go inside, and this access card will tell the machine that somebody is inside, and they will immediately, the beam will be shut down. So this kind of accidents cannot happen at all. And I remember somebody from Bhabha Atomic Research Center, he actually was inside and the beam was turned on. So after that, we set up in TIFR, we set up 3 alarms. So if the 3 alarms are put on, and these alarms will sound for like 5 minutes, and then only everybody goes out, and then only the beam is started. After that, this sort of events, this sort of technique was used. But nowadays in accelerators like CERN, it is fully mechanized. There is no way that people is inside and then the beam is irradiated. There is no way to do that. So immediately, if somebody is inside, online, the machine people or online, the machine itself will understand that somebody is inside, so it will not start the beam at all. But in university labs in the United States, it may so happen because it is fully manual, and the students, postdocs, and professors, they run the accelerators. There is no separate people to deal with that. But then you learn a lot of things: how to run an accelerator, how to do everything on your own, everything. So you know every aspect of it. But in national labs in the United States, like Argonne National Lab or Michigan State University National Superconducting Cyclotron Center or CERN, they don't even allow you to touch. Okay. In CERN ISOLD, we can at least control the beam that is falling. We can control at night, because in the daytime there are accelerators. In the night times you have to run it yourself. In ISOLD, in the radioactive ion beam facility. But this huge ring in CERN where the proton beams are coming, those are run by trained people. You are not even allowed to touch any button. Okay, but in American universities, you have to do it yourself. So that's the only way to learn. Otherwise, you don't have a feel how to run an accelerator. Anyway, so bombarding neutrons is very dangerous. And if you are irradiated with neutrons, that is very dangerous compared to alpha particles or protons. Okay, because neutrons are neutral particles, so they can penetrate deep. Okay, so you have radiation therapy for cancer treatments also. So basically, they irradiate this. Now I think there is carbon-12 irradiation, so that they pinpoint in such a way that they hit the tumors. So if you study nuclear physics, there is a huge prospect that you can go to medical physics, radiation physics, and I know many people who have changed fields and they are earning millions of dollars nowadays, because this cancer treatment by radiation is a huge business. So they deal with it. In the US, there are a lot of nuclear physicists who have changed fields to medical physics, and they are now people who determine how much dose needs to be irradiated to cancer patients. Okay, so where was I? Okay. Okay, so if you bombard this proton, neutron, etc., so that can actually get absorbed by the nucleus. And this nucleus, what happens if the nucleus absorbs some bombarding particles like proton, neutron, so that momentum will be shared by all the nucleons, because it is not that inside the nucleus that momentum will be shared by one particular nucleon. It's not like that, because it's close packing. So all the nucleons will share that momentum. So that nucleus will get excited and make some kind of compound nucleus, and then this compound nucleus might start emitting other nucleons. So the nucleus as such, the density of the nuclear material is almost constant, and that the binding energy is roughly proportional to A. That you have already seen, because you have plotted the binding energy versus nucleon curve, and that is constant in the middle of the curve. In the lower side it falls, and also in the higher side it falls. So the state of the nucleus is comparable to that of a solid or a liquid matter. But actually it's not like a solid, but it's rather like a liquid. More likeness to a liquid, as the particles in a nucleus are not arranged in a regular crystal-like structure. And its 0 point energy is too strong in comparison with the potential energy of the forces and keeps them in a state of disordered motion. So it's more or less like a liquid drop. So have you played Holi with these balloons? Have you all played Holi? You have these water balloons. Do you understand? Water balloons?
Yes, sir. I never
Yeah.
played
So
Holi,
it,
but I can imagine.
what?
Sir, I never played Holi, but I can imagine.
Oh, you can imagine, but it's these water balloons. Understand? You can catch it by your hand, and then it's very hard. Then it might break. All the water comes out. So this nucleus is more or less like that, some kind of liquid drop. Okay, and you have seen that this binding energy is proportional to the number of nucleons inside it. So it's a kind of a drop of a liquid. Uh, this idea of the liquid drop structure of the nucleus and that the drop has a surface and is electrically charged influence the total energy, that is the mass. Okay, ultimately this binding energy and mass, all these things are related. Okay, now you have kind of tables in nuclear physics where all the masses of the nuclei are tabulated. So the technology of accurately measuring the masses of nuclei is known as mass spectroscopy. How to determine the mass of a nucleus? So actually, since it measures the atomic mass rather than nuclear masses, it is conventional to represent the results in the form of atomic masses. What's the difference between an atomic mass and the nuclear mass? It is just the difference of the Z electrons, and that's the difference. And you have seen the plot of binding energy per nucleon is nearly constant in the middle and falls off at small and larger mass numbers, that is A. And the curve is peak, that is the maximum binding energy only in the middle where there is iron. And so that's the reason why there is large abundance of that element in nature. So because iron is the most stable, that is the most maximum binding energy. Now that this sort of liquid drop structure, that actually using this liquid drop model, we could derive a semi-empirical mass formula. You have a mass formula for the mass of a nucleus. The nucleus is treated as an assemblage of interacting particles, similar in some way to a drop of liquid. That's why it's called a liquid drop model. With Coulomb forces, obviously you have a charged liquid drop, and effects of the Pauli exclusion principle and other corrections. So first, in that liquid drop model, the semi-empirical mass formula, the first term that is important is the volume term. But you already know that this term will be proportional to the number of nucleons. So you have this B is equal to QVM capital A, where QV is the heat of vaporization. You just compare it with liquid drops. The heat of vaporization, if you heat it, it will vaporize. And mm is the mass of each molecule and A is the number of molecules. It is similar to that. So in case of liquid drop, you have B is equal to QV mm A. Similarly, in case of nucleus, we can have the binding energy, we can have the binding energy BV is equal to some constant V times A, which is just proportional to the number of nucleons. You can remember that it is not A square, okay, because it's saturated. If you remember long back, it is AC2, but it's not proportional to A square. It is proportional to A. So because it is short range forces, that's why it's proportional to A. It's not proportional to A square. So you have the binding energy, which is proportional to the mass of the nucleus. So the first term, this is the volume term. The next term comes out the surface term. So you have, depending on the surface, if the surface is small, the binding energy will be small. That's why you have in the lower side of the binding energy curve, you have the binding energy falls off, because you don't have a proper big surface, because the number of nucleons is small, right? So you have this, and the surface is proportional to A to the 1/3, A to the 2/3, because it's proportional to R square. So which R is proportional to A to the 1/3, radius is proportional to A to the 1/3. So the surface R square should be proportional to A to the 2/3. So the surface term is proportional to A to the 2/3. Also, you have a Coulomb term. You have calculated that Coulomb forces tend to disrupt the nucleus. So you have a Coulomb term which reduces the binding energy, and you know that it's 3/5 z into z minus 1 e square. We have already deduced it in the start of our lecture series. You have that also. Also, there is some kind of symmetry term. If there is symmetry, that is the number of neutrons is equal to number of protons, then the binding energy is very low. But if there is asymmetry, that is any number of neutrons or number of protons is more, then there is this asymmetry term which is proportional to n minus z square. So that reduces the binding energy. Also, there is some pairing term. So for even nuclei, the nucleus is mostly stable. So you have this plus delta. And for odd nuclei, it is minus delta. So the complete formula can be given by this expression. So basically, if you have all these constants from systematics, and if you have the charge number and the mass number, so you can calculate the binding energy. Now, what is binding energy? Binding energy is just the mass of the nucleus minus the mass of the constituents, which we have studied long back. What is binding energy? So basically, from the binding energy expression, you can calculate the mass of the nucleus. So this equation, the last equation of this slide, this equation is known as the semi-empirical mass formula. So basically, you can determine the mass of a particular nucleus MZA from this information. Is it clear to everybody?
Yes, sir.
Okay,
Yes,
so
sir.
I will stop here. I will stop here, but don't worry. I will revise this liquid drop model in the next. I would say I will meet you in next year. So I will start with this liquid drop model because now I just gave you a little bit about the concept. I will send the lecture notes, and I will start with liquid drop model, and then I will move to nuclear reactions, and then we will close off, and then we will revise some of the stuffs of the lecture series. So, are you all enjoying the course? I mean, do you understand what I say?
Yes, sir.
Yes,
Yeah.
sir.
Okay. Okay. So I will give you some more problem sets, and I will wait for your answer scripts, and then I will send the solution sets. And so enjoy your holidays. So I will meet you. I mean, so 30th is another Wednesday. So I will not take class on 30th. And so basically, I will meet you. I think on which date? In the next, either 5th or 6th. So enjoy your holidays, and study a little bit, revise. I would say make revisions a little bit, but enjoy your time. It is very difficult to go out nowadays since you have another new strain of coronavirus coming up. So it is better to remain safe, and I mean, not to go out too much. Mostly you interact with your friends over phone or Google Meet or Zoom or whatever, or WhatsApp, and enjoy your time. Take some self time, I would say, self evaluation. Think about, read storybooks, enjoy cinemas, movies, like that, and stay healthy. Try to keep your health in good terms, because nowadays if you have to go to hospital, it is very dangerous. God knows what will happen, and there are so many people in both institute. I have heard so many people inflicted with COVID-19, so it's a real problem, and we are
Yes.
facing, because sometimes I had